Good morning, everyone, and thank you to the organizers of the Long Island Natural History Conference for inviting me. I've been talking about the Great South Bay's new inlet virtually from the day it was formed. So, and these are sort of rolling talks with new evidence included and some of the older stuff sloughed off because one can't talk for 6 hours. Today's talk is an update of the latest report, which was put out in June. A new report is just about to be released. But even though we haven't been reporting and publishing the results, we've been going out and visiting the inlet at least on a monthly basis throughout the summer and now into the fall. One of the interesting features about this study is that we've been observing Great South Bay in some detail for 8 years prior to Sandy. And so that actually gives us a reasonable basis for comparison, which is a bit of an unusual situation for these barrier island situations. As Carol mentioned earlier, they had to hustle out and try to get some pre-Sandy information. And that's one of the few times that that kind of data is available. And as far as I know, the kind of data we have for Great South Bay is the only time that's been available for any of the longshore coastal lagoons. And it's important to realize that coastal lagoons are the dominant shoreline feature from Cape Cod to Mexico. And so there's a need for a good deal more research in this area. The other aspect here on this slide is that there have been a number of people who have contributed. Some of these, or actually most of the people listed there, are unpaid volunteers, and so we need to thank them. So we're going to talk about briefly the dynamics of Great South Bay and briefly how that impacted the storm and why the breach was formed. And then we'll talk mostly about the evolution of the new inlet, and then we have some measurements of the bathymetry and the velocity. Most recently, we've made some velocity measurements to understand the transport of ocean water and bay water through the breach. And then we'll look a little bit at salinity and changes in the ocean bay exchange. You all know about this, but Great South Bay is about a 70 or 75 mile extent from Smith Point to East Rockaway Inlet. The average depth in Great South Bay is only about 2 meters, so it's a pretty shallow region. The area is impacted by tides, and as the eastern portion of Great South Bay, which is the part that's illustrated here, is dominated by Fire Island Inlet. And Mauritius Inlet to the east has some impact, but Jones Inlet and East Rockaway Inlet are not really major players in this area. So this is a complicated area. It's at least a 3-inlet lagoon, which makes it very complicated from a dynamic point of view. Typically, when one has multiple inlets to a lagoon, that's not a stable situation, and almost always one lagoon wins out. Clearly, Fire Island Inlet is the big one, and so ultimately it will win, especially since it is defended with bulkheads and dredging. The aspect here I wanted to just sort of emphasize is that the Great South Bay responds differently to wind events depending upon which direction they go. There's two parts of their response to the winds. One is a very local and very quick response in which the wind blows the water downwind. And so there ends up with a slope in the downwind direction, slope up in the downwind direction. So there's a setup downwind. And that happens very quickly. And the next slide shows that. The other response is more gradual, and that is when the ocean responds to the wind. And it takes 12 to 24 hours for the ocean to respond, and it takes another 12 hours or so for the bays to respond, for the ocean water to come in or to the ocean goes down and the bay water to escape. So so the secondary response to the wind is the ocean response, and that takes about 27 hours in Great South Bay. And that's illustrated in this diagram. This is a correlation diagram, which might not make too much sense to you, but this is the direction in which the wind is blowing. So this is sort of opposite what you hear from the meteorologist. So this is the direction toward it's going. And blue is negative and red is positive. And so here in the lower one, this is the along bay setup, and you get a maximum response within a couple of hours of the wind being turned on. And in the bay, the wind, the setup is in the downwind direction. So for instance, in a nor'easter, Lindenhurst has high water, Bellport has low water, very quickly after the winds turn on. The ocean, on the other hand, works in the opposite direction. When the winds are along the shore, with the shore to the right, the ocean rises. When the wind is along in the opposite direction, in other words, from the west toward the east, the ocean drops. And so that's why there is a difference between the local setup within the bay for a easterly wind, a wind going toward the east, and there would be a set down in the whole bay as a result of the ocean for the same wind. This situation over here is the nor'easter impact. So the bay ultimately goes up, and the slope is, in this case, the way it's defined is negative. So Bellport goes down and Lindenhurst goes up. So that's how the bay basically responds. And that's how the inlet was formed. The winds were strong out of the east, and so it blew the water down toward Lindenhurst and built up water on the offshore side. And so it climbed up the dunes, and on top of this are the waves. And Carol showed a very nice picture of the wave climate. And so they begin to overtop, and there's a big height difference between the water on the bay side relative to the ocean side. And once just a little bit of a trickle starts, that height difference will just saw a way through with the inlet, and that's exactly what happened during Sandy. This is what the old inlet area looked like prior to Sandy. This is the old inlet. These are the back island dunes that were, or back bay islands that were formed when the old inlet was there. It closed in 1825, and it had lasted for about 60 years. And it was a big one, big enough for real ocean-going ships to use it. And in fact, Bellport was founded with the idea that they would make ocean-going ships, and they would have access to the ocean just 2 miles away. It closed in 1825, about 10 or 15 years after Bellport was founded, so those plans sort of had to be adjusted. The inlet formed right through here. This is the old inlet dock and the walkway to the beach. And this is an old place where boats were moored when there used to be beach clubs here. And this is where the breach happened, right through here. So we've been taking some aerial photographs, and sometimes this is one of the flight tracks. We go back and forth, try to map what's going on with the video camera. But the first few flights were all, we only were able to take sort of oblique photos. So this one was 4 days after the inlet was formed. And you can see that, well, there's the remains of the dock, and the inlet is pretty straight across, and it has an entrance to the east over here. There's the sand island here, and it shortly thereafter, there was a sand island that went all the way to Pelican Island, and there's the gun club house that had been there for 50 or 60 years, and and it didn't survive all this things that are going on here. Here's a brief set of more oblique shots showing, here's this sand island that connects Pelican to the western part of Fire Island. This was after a bit of a nor'easter, and so already the morphology of the inlet has changed. A week later, another storm went through. It blew through the sand island, and so we have now what we call the west channel here versus the east channel. And there's been a battle between the two, so to speak, as to which one is the dominant one. At this point, the east channel has won out, but one can't count on that forever. The other issue is that the inlet has migrated to the west, and this is some of Patty Rafferty's along the low tide line walks with a GPS recorder, and this blue line here is essentially that one, and you can see, and the picture here is also, this is I'm not sure who took this, USGS probably. And that's where the breach initially was, and you can see that really just in a couple of months it had already started to move west. Here's some further walks. These are in March and April, and there's clearly been a long movement. I don't see, down here you can hardly see it. That's the length scale. So this thing has moved almost 100 meters to the west, and the other side has kept pace. Well, actually, this side has kept pace with the westward erosion. You can see that there are these areas of bush and brush, and so what happens is that during the migration, if there's sand here and no brush, then the western migration is fairly quick, and then it sort of stalls as it has to chew its way through another pile of brush and roots, and then it jumps again. At this point, the western boundary is about here, and the eastern boundary is about here. Okay, so this one goes through August, and it shows, among other things, the retreat of the western side and the formation of a spit, a sand spit on the western part of the thing. And this is a major item because it's going to change the configuration of the inlet, as you'll see. So by February, we were able to take some videos and stitch them together into photo mosaics. And so now we have a real vertical view of what's going on. And among the other things that are not only the inlet itself, but you can see here the Back Bay shoals that have been formed. They're really quite extensive, and for the guys who go fishing out there, you know that it's really quite shallow. There are some channels that you can work through. You know, they might have 1.5 meters of water, but a lot of this stuff is well less than 1 meter deep, and oftentimes at low water you can see all the birds standing on these dunes. So if we go into June and off to September, you can see the development of this spit on the western side. Some of these sand islands are now getting even more permanent and constructed. You know, they actually have things that look like brush on them, but those are carried on by flooding waters and deposited there. In fact, right now there's a tree here that looks for all the world like it had always grown there. And I don't know how it managed to get there right side up and buried. But anyways, and Pelican Island now is about a third of the size that it was. The osprey nest is secure. It's still working fine, but the house has long since taken a hike. Now, the last two slides here on the overflight happened after an early October, not really a nor'easter, but a period of significant easterly winds, winds from the east. And that's all of a sudden changed the behavior of the inlet. It had been fairly stable through the summer and from the late spring through the summer. And then this thing happened. It was about 5 days of easter winds from 15 to 20 knots. 15 to 20 knots is usually not a big deal in Great South Bay. We see that virtually every day during the summer. But it was coming from the east, and it was had a long duration. And it further eroded the western side. It changed the shape of this western spit and started moving it northward. Prior to that storm, the extent of the spit was about here. And so it's moved. This is each of these ticks is 100 meters. So it's moved almost 100 meters north. And then a few weeks later, it had extended even further. And now the east channel, which used to be fairly substantial through here, is now constrained to this fairly small area, less than 100 meters across, with a lot of sandy area just to the west of it. And so this has now been fairly restricted. And the east channel is now the dominant channel. And yeah, so the other thing to focus on here is that the behavior of inlets and these kinds of things, they start straight across the island. And then through erosion on one side and literal drift of sand on the other side, the inlets migrate west and rotate. So this inlet is now nearly going north-south, and it started perpendicular to the shoreline. And so you can see that that's well developed at this point. The other issue is that for a long time, the deepest part of the inlet was right here. The extension of these spits has moved the main channel, and the deepest part is now just a little bit northeast of the dock, and that's all that's left of the dock, which is the T on the dock. So we've been doing some bathymetric surveys with our high-tech equipment, and it actually is pretty high-tech. We use a RTK GPS unit that it can tell you where you are, both horizontally and vertically, to within 2 or 3 centimeters. And so I'll show you some of that data as well. So this is the kind of bathymetric surveys we do. We try to make a number of excursions in and out of the inlet, and then a lot of them going back and forth, trying to define the deepest area and the cross-sectional area here, which tells you the admittance of the inlet in terms of the transport of water from the ocean to the bay. This is the survey on November 7th, 2 or 3 weeks ago. And you can see that now this spit has gone, and the deepest spot is now here. So here's a latitude line. Here's the same latitude line. In May, the deepest spot was down here, and now it's up here. And so this, and you can see that the whole thing is beginning to really lay over and get, the whole inlet is now getting bigger, longer. And ultimately, the extension of the inlet will cause its demise. It gets so long, so skinny that it can no longer keep the sand from depositing, and then some event will come along and it'll snuff it off. So here's all the bathymetric surveys we've done. The box is the same box in all these pictures, and so you can see the changes in orientation and the westward movement. And so now, for instance, well, the last bit, it's all oriented essentially north-south. It's moved west, and now it's even further west, but it's extended north. The black line is where I've measured the cross-sectional area of the inlet, and you'll see in the next picture the development of the cross-sectional area. That's an important criteria for showing how much water can actually get through the inlet. It was easy to do it because we went from shore to shore over here, but now it's not quite so clear where the shore to shore is, so I went from the shore here to a shoal in the middle of the opening here. This is the dock, this black square, or black X. This is the cross-sectional areas. This was probably a better diagram earlier on when I had fewer of them. But anyways, this is where the cross-sectional area started in December, way over here. And it was only a little less than 2 meters deep at the deepest spot. Then as time went on, it has gotten deeper, clearly. It's also moved to the west. At the maximum depth we've ever seen is a little over 7 meters. That's a little over 22 feet. And then for most of the summer, it was somewhere around in here. And now the November one it's moving back to the west, which is basically means that it's moved north in this slanted picture. The cross-sectional area has, as I said, this is an important number. And initially, the inlet was relatively small, less than 100 square meters. It quickly grew. Until the end of February, it was around 400. And it is oscillated, which is probably as much the measurement variability. But 400 seems to be about the stable size of this inlet. And then this is the estimate we've made just recently, and so it's dotted because the criteria is a little different from the rest of them. So basically, even though the inlet was undergoing a whole lot of changes, it was changing shape, it was changing its position, it was rotating, its essential dynamics were remaining the same. So it was stable from February, basically, at least through this early fall. What happens now is a little, no guarantees as to what's going on. But the assumption is that the inlet is only made of sand, so it's easily eroded. So what is the limiting factor? My assumption is, at this point, it's the back bay shoals that have been formed, and that's what's limiting the access of the ocean to Great South Bay, and therefore keeping the inlet about the same size. Now one of the big questions was how much water is actually going through the inlet, and so we've done a velocity survey recently using our little skiff, and we've put an acoustic Doppler current profiler, which is this gadget here. It's a 1200 kilohertz device. It uses the Doppler shift it sends out a pulse, and it receives a Doppler shifted return. And from that, you can figure out how fast the water is moving relative to the boat. And then you have to navigate the boat rather precisely to back out the boat's motion in order to get the water velocity motion. And so that's what this device has done. We did a survey, and we picked the spot where the shoreline was fairly steep so that we could get as close to the shore as possible on both sides. And even though the main channel, the deepest spot is over here, it's unclear where the western end is. So we picked this spot. And we went back and forth about 70 times. So we have a lot of data to look at. And some of the data doesn't work out, but this is what it looks like if this is the backscatter, so this is the bottom. The backscatter acoustic thing, so it's basically what your photometer would show. And you can see that this is the shape of the bottom as we go from west to east and then turn around and go from east to west. Down here are the velocities. This is the north velocity, which is the main component going through here. Here's a set of all the near surface velocity vectors, although I've taken out all the ones from here because there's so many. Maximum currents that we saw are about 4 to 5 knots. It's an interesting feature. Clearly, the main flow is right through this main channel here. Some flow is coming in from the west channel. It comes in and it's heading east, and then it rotates around. And it turns out that there's an eddy right about here that is very prominent because we were stemming the current as we are over here on the east side. And as we went over to the west side, we actually had to turn the boat around and stem the current from the opposite direction. So there's a very clear eddy here, and it probably, there's sort of a negative shape to the shore here, and so there's probably eroding some of the shoreline here, and that's leading to the extension of the spit. The main outflow current, this is all during ebb tide, is off here to the west. Very clear. This is, out here is the ebb shoal, and with breaking waves, and it got really quite shallow. Over here on the right is, if you take the velocity through that section and you add it all up and multiply times the area covered by each of those things, you can estimate what the total transport of water through the inlet is at any one point. And so on the left here, this is the transport in cubic meters per second. We got there at slack water after a high in the ocean, which is there's about a 3-hour delay. And we stayed almost to slack water at the after low. You can see a couple of things here. One is that the maximum transport is about 450 cubic meters per second, quite a sizable number, but small by comparison to Fire Island or any of the big inlets. The other point you'll notice is that it's not symmetric. And that's because the ocean and the Great South Bay are not going up and down together. The ocean goes up and starts coming down, and Bellport, the Great South Bay, is still going up. And so there's sort of this syncopation between the ocean and the bay, and that leads to this asymmetry. When you add up all the transport through the entire ebb cycle, it turns out to nearly 7 million cubic meters. And so it's important to figure out what that means in relation to the bay itself. So what the typical way one deals with that kind of a question is you look at how much of an area of Great South Bay, how much area can this transport deal with the tidal needs of the bay. And so the tidal range that day was 0.4 meters. And so if you divide that into the total transport, you get an estimate of the area that is for which this inlet is responsible for the tides. And it turns out to be about 17 to 18 square kilometers. The area here in red, Bellport Bay itself, from South Howells to to the island and over to Smith Point is about 18 square kilometers. So the inlet is able to essentially deal with Bellport Bay's tidal needs. The Great South Bay total is about 220 square kilometers. So the inlet is about 8% of the larger area. And so, as you'll see later, anyways, that's sort of the limit of the impact of the inlet on the Greater South Bay. It's about 8%. We've also been measuring some of the water properties, and we've had the Great South Bay Observatory has been going for about 8 or 9 years now, and we have a series of instruments deployed along the coast, and we have a buoy here south of Sayville, and from that we can measure the tides, tidal range, and the tidal phases at various locations. Bellport is the one that is, of the locations that we have, Bellport's the only one that's actually had any effect at all. Before Hurricane Sandy, the amplitude, which is about half the range, associated with the main semi-diurnal constituent, the 12.42-hour constituent, was about 0.16. So the range associated with this thing is about a third of a meter, or about a foot, which is just about what you typically see at Bellport. And the phase, which is in terms of degrees here, is 102. After the hurricane, the amplitude is the same, the range is the same associated with this tide, and the phase has moved up by equivalent about 20 minutes. So the other locations, there wasn't any noticeable particular change, statistically significant. So far, the inlet, that's the only impact of the inlet in terms of tides. Okay, so, right, so one of the major issues is the exchange of water. And so I'm going to show you a record from Bellport and a record from the Great South Bay buoy, and at which we measure winds. By the way, that's the only place that winds were recorded during a hurricane. Every place else lost their power and don't know what the winds were. The buoy is the only place that we know where what the winds were. So here's a record. Top one shows the Bellport sea level data. Here's Hurricane Sandy, and if you look at these are the 7 events that Cheryl pointed out as where the offshore winds, offshore waves were high. So this is most of these are nor'easters. This is the annual cycle of temperature, but this is the impact of the inlet on Bellport's salinity, which is an indicator of the exchange with the ocean. So immediately as the inlet opened, the salinity jumped about 6 parts per thousand, which is in oceanographic terms a huge number. And it has remained something on the order of 28 to 29, and it varies depending upon what's going on elsewhere. But it's all well above the historic norm, which is about 24 parts per thousand. And this one shows the impact at the buoy as well as at Bellport. South of Sayville, the salinity is typically about 27, and it jumped up for a little while, and then it climbed beginning in March. So this is the impact on sort of the western portion of the Great South Bay. They started dredging Fire Island Inlet in February. So it's quite possible that this is the result of that. This enormous dip in salts everywhere is because of a 9-inch rain event that we had in June, and that dropped everybody's salts down. At this point, Bellport is around 28, 29 parts per thousand. And the buoy has recovered. It's also around 29 parts per thousand. So this inlet and presumably the dredging in Fire Island Inlet has changed the chemistry of Great South Bay rather substantially. And one of the impacts has been the decrease in brown tide. And so there was a brown tide bloom in Great South Bay this year, but it was very short in Bellport Bay, lasted a little longer here. But in general, the whole thing was less than we've seen in the past. The other issue is flooding in the area. And certainly the people in the western part of Great South Bay are concerned about the flooding. They all live in relatively low-lying houses, and so any extra water is not a good thing. So we've looked at what is going on. How come there seemed to be so much extra flooding in Great South Bay this year? And so we looked at not only the water level records in the bay, Bellport and Lindenhurst, but we've also looked at some of the sites in the Mid-Atlantic Bight, Atlantic City and Woods Hole, and down here is Chesapeake. Chesapeake, Atlantic City, and Woods Hole all show essentially the same thing, and they all show that when we had floods in Great South Bay, the entire Mid-Atlantic Bight was going up. And similarly, when the Great South, with the Mid-Atlantic Bight going down, so did Great South Bay. This is the event that got a lot of the politicians excited, and they held press conferences about how terrible life was. But if you look at it, Woods Hole, Chesapeake, Atlantic City, everybody went up. So, and if the ocean goes up, then the bay's going to go up. There's no way you're going to avoid that. So this is something that was, it occurred over 1,000 kilometers, and not just within Long Island. And at the same time, these people, the politicians were concerned on Long Island. Politicians in New Jersey were equally up in arms. So this is a brief summary. Although the inlet has increased in size and moved west, it seems to have stabilized. This extended spit is changing the morphology and extending the inlet off to the north and northeast. The inlet is relatively small. It's less than 10% of the cross-sectional area of the combined Great South Fire Island Inlet and Mauritius Inlet, and it's responsible for less than 10% of the tidal exchange. There's clearly been an increase in water exchange, and it has clearly improved the water quality and clarity, and it has reduced the brown tides. Last year we experienced unusually frequent storms, but not historically exceptional. If you look back in the records, water levels in Great South Bay have reached these levels many times. And there's these anecdotal things that, I've lived here for 30 years and I've never seen it like that. Well, that's not true. That happens quite often. And the bay matches the ocean at the low frequencies and with a delay. But the inlet itself is not the responsible player. So, thank you very much.
You'll have time for questions. I know you may not be able to answer this question, but can someone in the audience perhaps comment on the effect on the fisheries in the Great South Bay?
I'm not a fisher folk myself, but I've certainly heard from a number of them, and they all say that the fishing, at least in the Bellport Bay area, is phenomenal. If you go out there, and any weekend there'll be 15 or 20 boats fishing in and near the inlet. Of course, the Park Service would prefer that you stay out of the inlet itself, but you're welcome to go into any of the areas in the back bay, and the fishing has been good. The clams are producing unusually large growth rings this year, and so from those perspectives, it certainly appears that the inlet has done good things.
Hi. If I interpreted your slide correctly, you had one slide where there was a box that went from Fire Island to Bellport and showed where the impact from the breach was limited to. So does that apply also to this slide where it says that the water quality has improved and it's clearer? Is it limited to that box as well?
Clearly, that's the most dramatically affected areas. And in fact, when we were doing overflights at the time when there was the brown tides, you could see the ocean plume of clear water and a very hard line between the ocean water and the brown tide. And that extended about 3/4 of the way across to the Bellport area. So there's an immediate impact in the near area. But it is clear, people in Patchogue Bay and further west have said that the water was clearer this year than it has been in years. And so while they don't get a daily pump, I think there is an exchange between Bellport Bay and the rest of the bay. It's not isolated. And so eventually that oceanic water is moving west, and some of that is showing up in the salts from the buoy south of Sayville. Jeff?
Has anyone been looking at the volume of sand that has been accreting in the shoals on the bay side of the breach? And has anybody been monitoring their growth and elevation and if they expected to go above sea level at some point?
Well, some of the photomosaics show that some of the back bay islands are coming up above sea level. I think they are formed when the whole area is flooded by a particular storm or something. The sea level goes up and it then moves the sand around. And then when it goes sort of back to normal ranges, these sand islands stick up. It's not been possible to measure the elevation of these things. Our little skiff only draws 18 inches with the motor down, and we can't go anywhere near them. So the only way we're actually going to be able to do this is if there's a LiDAR survey, which is a light that shoots down, and you get a reflection from the sea surface, and then you get a secondary reflection from the bottom. And the USGS, I think, did a LiDAR survey of the land shortly after after Sandy. You can do the same thing in the water, but it hasn't been done at this point.